Welcome, Calculus AB. This is section 3.1, Extrema on an interval. The essential question is, what's an extrema? Let's begin. So in this lesson, we're going to go over three goals. First, I'm going to understand the definition of an extrema of a function of an interval, understand the definition of a relative extrema on an open interval, and find an extrema on a closed interval. So let's walk through that. So the first thing I want to do is figure out what the definition of an extrema is. And your textbook has this definition right here. But basically, it's the high and low points on the function. So this minimums and maximums for certain intervals here. But it's the highs and lows points. And there's different types of extrema down here. We have the extreme, we have the absolute minimum, the absolute maximum, global minimums, global maximums, endpoint extrema. So it's the highs and the low points, okay? It's the extreme points. So we can do a lot of things, and we try to find those points because those help us out. So let's look at some functions right here. I have three different cases of a function. It looks a little different in each case. In the first case, it's a closed interval. When I do brackets, -1 to 2, this means x going from -1 to 2, but also including those numbers. This has some extrema here. The extrema are going to be at the ends here, -1, -2, and 2, and then down here. This is our minimum. And then we're going to, up here at 5 is going to be our maximum. So those are our min and max here. Those are two of the extremes. Now, in this case right here, we're on an open interval. So open means -1 to 2, but not including -1, -2. So in this case, I only have a minimum right here at 1, but I don't have a maximum. It's getting close to this, but not hitting this. Because it's not hitting an actual point, we do not have a maximum in this case. It's kind of weird, I know. In this case right here, so we have a maximum at this point because it's a closed interval from -1 to 2. But in this case, at that spot that usually is our minimum, it's a piecewise function, we actually go up to 2. There is no minimum here, it's an open hole. So there's no minimum, but we do have a maximum still at 5. So these are similar functions, but there's different ways to find those maximums. And we have an extreme value theorem. So if f is a continuous function on a closed interval, then f has both a minimum and a maximum. So that would be this case right here. It's closed interval, it's continuous, because you can draw it with one line without picking up, and it has both a minimum and maximum. In these cases, they're not closed, they're open on both ends. In this case, it fails the pencil test because you can't draw it because you have to pick up to hit that dot. So that's why it doesn't have that. All right, moving on. There we go, relative extrema and critical numbers. So we have this concept of a relative extrema. So if I looked at this function here, this is x cubed minus 3x squared. And if you graph this, it would keep going down forever this direction. It keeps going up forever this way. So the function's looking like this, and you might say, well, there's no maximum because it goes up forever and down forever. But we have something called the relative extrema. Where our relative maximum mins, they happen at specific intervals. So right here, you can see that we kind of go to the top of a hill right here. So this is a relative maximum. And down here, we go to the bottom of a valley, so this is a relative minimum. It's not the absolute relative maximum minimum because we know we go down forever, but we have relative maximum minimums. That's important. So what's a derivative at a relative extremum here? So let's look at this graph right here. I have a relative maximum at 3, 2, and it's this function right here. I'm going to find if my f of x is this, what's the derivative of x prime of x? Well, we're going to use the quotient rule here on the top. And the top, the f prime is going to be, it's going to be 18x for the top, and g prime is going to be 3x squared. So now the derivative of this is going to be is f prime, so 18x times x cubed minus 9x squared minus 3 times 3x squared all over x cubed squared. So at that point, I'm just going to plug in here. If you actually plugged in x, I want to find whatever my f prime is, so I'm going to find f prime of 3. And if you plugged in 3, you'd get 18 times basically 3 to the 4th power minus 9 times 3 squared minus 3, so that would be 3 squared minus 3 times 3 squared. Oh, that's looking like a mess, huh? All over x to the 3rd squared is going to be x to the 5th, so 3 to the 5th power. And if you did all this, actually it's not 3 to the 5th power, it's 3 to the 6th power, my bad. And if you evaluated all that and plugged that in, it's going to come out to 0. Okay, Let's try another example down here. So I have the f equals f of x is sine of x, so the sine function. And my relative maximum minimums are right here and here. What is the derivative at those points? You know, you might be able to look at the graph and figure this out anyway. So you know f prime of x in this case is going to be cosine of x. So at this point, let's try f prime of pi over 2. That's going to be cosine of pi over 2. And cosine of pi over 2 is the x values at pi over 2. That is going to be 0. Let's try the minimum right here. F prime of 3 pi over 2 is going to be cosine of 3 pi over 2. And if you're looking at your unit circle, that's going to be 0. So the derivative at each of those relative minimums and maximums is going to be 0 in those cases. Now, what's the derivative about? What about this one? So we have the absolute value of x. And this is a relative minimum here. But if we try to take the derivative f prime of x, this does not exist. You can't take a derivative of absolute value function right here. So the derivative at that minimum does not exist. And so we know some derivatives don't exist and some are zeros. So what we can do is, these are all critical numbers here. This is where x values, where the derivative is either 0 or does not exist. So sometimes we want to find these critical numbers. And here's two cases. In this case of this graph, we're both coming to this point right here, but there's not going to be a derivative at this point. In this case, there is a derivative. It's 0. It's a horizontal tangent line. Now, what can I do with these derivatives? I can use this to find the extrema on a closed interval. So this is what we're all leading up to. So here's the guidelines for this, and we'll walk through some problems. I want to find extrema on a function. I got to find the critical numbers of the function. And to find critical numbers, it's where the derivative is 0, so f prime of x, wherever that equals 0 or does not exist. And then you want to evaluate each of those critical numbers, and also evaluate the endpoint. So you want to find f of a, and you want to find f of b. So those are the two endpoints there. And the smallest value is the minimum, the greatest value is the maximum. So how do we organize this? There's a lot of steps here. So let's walk through some problems. I have this, I'm going to find the extrema of this function on the interval -1 to 2. So first thing I'm going to do, if I'm working on this function, I want to find the critical numbers. So I'm going to find f prime when it's 0 or does not exist. So let's find f prime of x. F prime of x in this case is going to be 12x cubed minus 12x squared. Okay? So I want to find out where this is 0, and an easy way to start this off is I'm going to factor everything. I'm going to factor out what I can. So what I'm factoring out, I could factor out 12x squared. I'll be left with x minus 1. So looking at my two factors here using the zero product property, the x values that would make this 0 when it's x is x equals 0. And for this case, x minus 1, that's going to be, f of x is going to be 0 when x equals 1. So when you're setting that to 0, those are my two values. And there's not going to be any values for x where this does not exist. So two of my extrema right here are x equals 0 and x equals 1. I'm going to make a chart right here. I'm going to the book does it differently. I'm going to do an xy chart right here. So it's going to happen at 0 and it's going to happen at 1. And we also have our two endpoints right here in the interval. -1 for x to 2. So these are my four extrema here, my two endpoints, and where the derivative is equal to 0. So what are my y values? Well, I'm going to have to plug it in this case. And if you're plugging in those y values for x, what do you get for y? Now on that first one, what you're going to get is you plug in -1, and I'm going to get 3 times -1 to the 4th power minus 4 times -1 cubed. And what you'll get for that is you'll get positive 7. Next one, when you plug in 0, you'll get 0 minus 0, which is going to be 0, because 3 is 0 power. And if you plug in 1, you'll get 3 times 1 to the 4th minus 4 times 1 to cubed, and that will be -1. And if you plug in 2, you get 3 times 2 to the 4th minus 4 times 2 cubed, and that's going to come out to positive 16. So my extrema in this case, we want to find the maximum and the minimum in this case. Actually, I just wanted to find those extrema. And let's label which one's the maximum and minimum. So in this case, my minimum is going to be -1. So it's going to happen at 1, -1. And my maximum is going to happen, well, y is the biggest there, so at 2, 16. And here's what the graph of that's going to look like. in this case, I have all my points right here. Boom, 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 boom. And we have our maximum at 2, 16, and our minimum's at 1, negative 1.